Hey everybody, so today's lesson is going to be looking at some patterns and then looking at how those patterns relate to rate of change, which we're eventually going to call slope. So we're going to look at our first pattern here. I want you to draw this pattern on your paper. We've got three figures here. We've got the figure number at the bottom, and then we've got what the figure actually looks like at the top. So I'm going to scoot this in a little bit closer so it's easier to see. All right, in figure one is made up of 4 sticks. So we got one box that's made up of 1, 2, 3, 4 sticks. In figure 2, we've got 2 boxes. Figure 3, we've got 3 boxes. And we need to figure out, our first question is, how many sticks would there be in figure 4? So if this pattern kept going, if we looked at figure 4, how many sticks would there be total in figure number 4? So go ahead and take a minute, see if you can figure out how many sticks there would be in figure 4. All right, so there's a few different ways that you could have figured out how many sticks are in figure number 4. The easiest way would be just to draw it out, because we know it's going to have 4 boxes. Going to have 4 boxes, and then you can just count the total number of sticks. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So in figure number 4, there are 13 sticks. There are four boxes, and there are 13 sticks total. That's not too bad. That's not as bad to figure out. However, a tougher question is here at the bottom. How many sticks would there be in figure 50? Now, you could go through and draw out 50 boxes, but see if you can figure out an easier way to do this. Look at the patterns that form with the number of sticks and the figure number. Think about how many boxes there would be, but go ahead and make your best educated guess as to how many sticks there would be in figure number 50. And give me an explanation on how you found that. All right, so I'm going to walk us through how we get that number. So the first thing I'm going to look at is the total number of sticks in each figure. Figure number 1 is easy. There are 4 sticks in figure number 1. In figure number 2, if I count them, I've got 1, 2, 3, 4, because I've got the original box, 5, 6, 7. So there are 7 there. In figure number 3, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In figure number 4, we already said that there are 13. So what would be the pattern as we move to the right? What is happening as we go up by 1 figure number? You should have said that we add 3 to each figure number. Each time we are adding 3. So there's that repetition going on. So if we repeat that over and over and over again, what is repeated addition called? You should have said multiplication. Repeated addition is just multiplication. So it's going to have to do with something multiplying by 3. How many times are we going to have to multiply by 3? Well, we would have to multiply 3 times 50, because we would have to add 3 50 times to get up to figure 50. So we would have to do 50 times 3, but we're not done there. Because in theory, that should work no matter what figure number you're at. But if I do that with my first figure and multiply the figure number times 3, that just gives me 3, and there are 4 sticks there. So I need to do 3 plus 1 more to get up to that total of 4 sticks. Same thing in figure number 2. If I multiply it by 3, because I'm adding 3 more sticks, that gives me 6. I still have to add 1 more to get up to 7. So to figure out figure number 50, a good start is this 50 times 3, which gives me 150. But then I have to add one more to get 151 sticks. So in figure 50, there are 151 sticks. Now, if you didn't get that, that's all right. We're just practicing with it, see if we can develop a sense for these types of patterns. Here is our next pattern. We've got figure 1, 2, and 3, and we got to figure out how many sticks there would be in figure number 4. Now, I think this one's a little bit easier, but see if you can figure out how many sticks would be in figure number 4 and explain how you got that number. All right, I think the easiest way to figure this one out is just to start counting them up. Each of these shapes has a hexagon in it because it has 6 sides. So this one has 6 sticks, 6, 6, 6, 6. If I add those together, I get a total of 30. Then if I move to the right, I'm losing one hexagon. So I've got 1, 2, 3, 4. 6 times 4, well, that gives me 24. As I move to the right again, this time I've only got 3 6s, so I've got 18. So in figure number 4, first of all, I would only have 2 hexagons. And if we think about which one we would lose, we would probably lose this top right one. So we would have 6 and 6, which would be 12. So in figure number 4, there would be 12 sticks. So my pattern as I move to the right, as I move from here to here, I subtracted 6 sticks. Here to here, I subtracted 6. I just keep subtracting 6 as I increase in those figure numbers. Now it asks, when will there be 0 sticks left? Well, if this pattern continues, how many would there be in figure 5? That's right, there should be 6 left in figure 5, and then if I subtract more again, in figure number 6, I'm left with 0 sticks. So after 6 figures, I'm left with 0 sticks. All right, hopefully you got that one. That was a little bit easier. I want to go back and I want to look at the original one that we were talking about. This one right here. So we had the figure numbers 1, 2, 3, and we said that each time we're adding 3 sticks. So I want to represent that in a table. So in my table, remember to make a table, we've got X and Y, but instead of X and Y, my input, I want that to be the figure number. So I'm going to do figure hashtag, figure number. And then my output is going to be the number of sticks. So if we look back up here at what our representation said, in figure number 1, that's where we're going to start. In figure number 1, there were 4 sticks. In figure 2, there were 7. In figure 3, there were 10. So my claim is that this relationship is a linear function. I'm going to go ahead and plot these on my graph. Go ahead and make a graph on your own paper. 1, 4. 2, 7, 3, 10. Now, this one's kind of a tough question. Why am I not going to connect the dots on this graph? So you could have had a lot of different answers. The answer I was looking for is if I connect them. Let's say, for instance, I connect from here to here. All those points on this blue line would then be technically part of our function, part of our representation. But if I look at a specific point, if I look at, let's say, this point right here, First of all, the coordinates of that point are about 1.5, 5.5. What do our inputs represent? Well, our inputs represent the figure number. Do we have a figure number of 1.5? No, of course not. We can't have a figure number 1.5, and we also can't use 5.5 sticks. So that means in this problem, we are not going to connect the dots. So anytime you're doing an application problem, make sure you think about, do I connect the dots on this one, or do I just leave it alone? If it's simply just graphing a function that they give you and it's not an application problem, then yeah, sure, go ahead and connect the dots. But for this one here, I'm not going to connect them. Is this a linear function? Well, we're not connecting the dots, so we're not really sure. How do we determine whether something is a linear function? There's two ways. The first way is, does it form a line on the graph? Well, we're not sure because we're not connecting the dots. The second way is we look at the rate of change. Is the rate of change consistent? And remember, to find that rate of change, I need to do change in y divided by the change in x. So for this one here, my first change in y is +3. My change in x is +1. 3 over 1 is equal to 3. Now I have to check, does it work as I keep going? +3, +1, 3 over 1 stays the same. The next one we talked about was in figure 50, there were 151. This one's a tough one. From 10 to 50, or to 10 to 151, to get there, we have to add 141. From 3 to 50, we have to add 47. If you type that in on a calculator, go ahead and do 141 divided by 47, and that also gives you 3. So it works, it keeps working, so we know it's linear. But does it go through the origin? Is it a direct variation function? Does it go through this point here? Well, here's how we figure that out. We know that the rate of change is 3. If I go back up to my diagram here, that means as I move from here to here, I add 3. But we want to go the opposite direction. We want to go from here to here. So the opposite of adding 3 is from here to here, we subtract 3. So in figure number 0, if we continue this pattern and we subtract 3, we would subtract 3 sticks and we would just be left with 1. So in figure number 0, we have 1 stick. So that means on our graph, it doesn't go through 0, 0, it goes through 0, 1. So this is a linear function because the rate of change is consistent. However, it's not direct variation because it does not go through the origin. So we can still find that rate of change even though it does not go through the origin. So what we're going to transition to is we're going to transition from calling it rate of change, constant of proportionality. We're going to start using slope. Where have you heard slope in another context other than math? Some of you probably said skiing, and that's a great use for it because slope in skiing describes the steepness of the hill that you're going down. Slope is very similar on a graph. It's describing the steepness of the line that it forms. Now, slope is going to be the same thing as rate of change, so we're still finding it change in y over change in x. However, we're going to change it up, do things a little bit differently. Normally, if I have a set of ordered pairs, because I've got the squiggly brackets, normally if that's the case, I'm going to make a table first. And I'm going to put it in my table. And then I'm going to find my change in y over my change in x. But what I want you guys to do is I want you to transition from, instead of going from here to here to here, to just skipping this table. And this is how we're going to do it. If we're trying to figure out what we need to add by to get from 12 to 24, well, to figure out what we need to add by, let's just subtract. We would just subtract 24 minus 12. That would tell us what we need to add by to get from 12 to 24. In this case, it is 12. Then our change in x on the bottom, same thing. How do we get from 5 to 8? We'll subtract them to figure it out. 8 minus 5 gives us 3. 12 divided by 3 gives us 4. So our final answer for the slope between these 2 points is 4. So the steepness on a graph, if you graph those 2 points and drew a line between them, it would be a steepness level of 4. And we'll talk about in the future what that represents and what it can represent in application problems. Now, this next part, I want to talk about writing down a formula that's going to work for you every single time. So I want you to put a star by this in your notes because this is super, super important. A lot of times students get confused by this, how this looks. All this is saying is given any 2 points, this is our first point. Points are written in x comma y. So this is our first x value. This is our first y value. This is our second point. So this is our second x value. This is our second y value. If we're trying to find slope, again, we're going to use m for this. If we're trying to find slope, again, we're looking for that change in y. How do we get from y1 to y2? What do we need to add by? To figure that out, we subtract y2 minus y1. The second y value minus the first y value. Then on the bottom, the second x value minus the first x value. So given any 2 points, if you take the second y value minus the first y value over the second x value minus the first x value, then you're going to get your slope. So here's a problem for you to practice on. You're given 3 points in this one. For slope, you only need to use 2 of them. So you get to choose which 2 points do you want to use. It's up to you. Go ahead and plug it into our formula, find the slope. Once you think you've got it, go ahead and type your answer in. All right, hopefully you got that our slope is equal to 5. Make sure that you've been taking really good notes on this. If you haven't been taking notes, go back and rewatch this. Because what I want you to do now is I want you to submit a picture or PDF of your notes to the Google Classroom assignment for this Edpuzzle. That way I know you've been paying attention and you've been writing this stuff down. So if you haven't been writing it down, you got to go back and rewatch it. Otherwise, have a great rest of your day. I'll see you guys tomorrow.